So, you know, we will not be meeting for lab on Friday because we have the Assurance of Learning Day. We're going to be doing that submax VO2 testing. Those of you guys that were at lab on Friday know what the potential extra credit opportunity you're doing is. You can feel free to share that with your classmates. I'm not going to. So you guys know what you need to do. And yeah, just make sure you follow the protocol when you guys are doing the walking on a treadmill. No zombie walking. So you can't hold on to the heart rate monitor thing and get the result from that because it makes the walking easier. So it's going to get your heart rate down. It's going to screw up your numbers. So instead you have to walk and then take your own heart rate while you're going, and or have a partner take your heart rate, or wear a heart rate strap, or if you have like you know, the Apple Watch, Fitbit, whatever takes your heart rate while you're going, you can go and use that method for how you're going to record. And then once again, you guys going to know your option for the extra credit. If you guys do the extra credit option, that's absolutely fine. I want you to go ahead and make sure you just submit those extra numbers. So you kind of like copy and paste the results from the lab, because you know you're going to be doing it twice and you know how. So any questions, comments, concerns about the lab expectations? And it's not going to be due until next week, but you guys got time. No questions. Cool. All right. So let's get into it and let's start talking about the joys of our cardiovascular system. And we left off talking about how we're going to redistribute our blood flow. Now, these two graphs are very important to understand, okay, guys? So the one on the left is showing as a percentage of blood flow. So you can see as you start working out, you are getting less and less blood flow to the red. Sorry, making sure I pull participants also. Perfect. Okay. So, which is going to be effectively our digestive tract, our kidneys, our liver. And so we're getting less and less blood flow there as we start exercising. However, when we look at that in absolute blood flow, notice when you're doing light exercise, you've got about the same amount of blood flow going to all of your digestive tract and your kidneys. But then we get to moderate, it's going to be a little bit less, and we get to really maximal exercise, it's very, very little. Now, the blue bar is your skin, so we can actually see that we get the greatest amount of blood flow to our skin when we're actually at moderate exercises, which is good because that's how we're going to thermoregulate. So at both light and moderate, we're sending a decent amount of blood flow to the skin, so we're going to be able to sweat things out. When we're at heavy exercise, we actually have less blood flow going to our skin than we even did when we were doing light exercise. And that's why when we're doing maximal exercise, it's so much easier for people to overheat. It's a very important thing to understand. Now, obviously, we're going to send a lot more blood to the muscles once we start exercising, both in relative and absolute sense. We are going to be sending the same amount of relative blood flow to the heart, because the heart's going to take 5% of no matter what it's pumping to itself, so it can oxygenate and be able to obviously contract and keep moving. Now, you're going to see how that's going to slowly increase when we go from rest up to maximal exercise, as you'd expect, because the heart has much increased cardiac output. And then finally, notice that the relative amount of blood flow to your brain is going down, but the absolute is actually staying about the exact same. We're not going to suddenly have less blood flow to our brain because we're exercising really hard. If that was true, you'd be in a lot of trouble. So, understanding this distribution shows us, A, we're doing a better job of sending that blood to the muscle, so you're going to be able to exercise at a higher intensity, and B, the big component of, yeah, you can risk yourself going into issues with obviously GI distress because you get less blood flow there, especially if we just had a big meal, and then we can risk ourselves having issues with thermoregulation if our exercise intensity is too high for what our body can handle in the given environment, how warm it is. Now, as we're sweating out volume, we are going to be actually decreasing our stroke volume. That is because we're sending more blood flow to our skin and we are sweating out that fluid, so we're decreasing our plasma component, which we're actually increasing our hematocrit, which makes our blood viscous. And since we have less venous return and preload, we are going to in turn have lower stroke volume, which means the only way to keep up our output is to increase our heart rate. So if you look at the graph on the right, you can see as you're exercising, you're going to be decreasing the stroke volume, which is essentially predicated by that decrease in blood volume, and also a decrease in our overall pressure. Now, notice our cardiac output stays about the exact same because we have to keep up that same work rate. It's going to be our heart rate that's going to go up because we're pumping less blood per beat. Now, This is an important thing because if you're exercising in the heat, it's going to come on even faster. And this is going to eventually lead to fatigue because obviously the heart is having to work much, much harder, and it's having to work against a greater amount of essentially resistance to the viscosity. So exercise and everything else in our body are always going to be, our body is always trying to maintain our wonderful homeostasis. We're trying to make sure we're oxygenating all of our tissues, and we're fighting for a very finite amount of blood supply. Now at rest, it's no problem because it's so easy for the body to keep up those outputs. But as we start going up and up and up and higher intensities, we're not going to be able to maintain blood flow to all of those tissues. And I'm quite sure you guys have had that moment before when you were trying to exercise in really hot conditions and you just couldn't exercise that well, or you had very little tolerance for it because you were sending so much blood flow to your skin, your muscles weren't getting as much, and just you fatigued out. Or you try to do a big meal and then you try to work out and then you had some horrible cramping because we're shunting blood away from our digestive tract to get it to our muscles so we're gonna be able to maintain our exercise intensity. Now, remember again, guys, with that AVO2 difference, so that's literally the amount of oxygen that we're going to be extracting from the blood as it's going from the arterioles through the capillaries back to the venules. And we're going to see that this is going to increase when we start exercising because we're literally going to do a better job of vasodilating to those individual capillaries of the muscles we care about that we're using and go to those fibers that are using energy aerobically. So we're going to be able to pull more oxygen. Now, this is a good thing because we're going to be more efficient. Now, notice, guys, when it says the mixed venous content is about 4 milliliters of oxygen per 100 milliliters of blood. And before, it was usually about 20 or so, maybe a little bit below that. Now, notice it says mixed. And that's when we get the blood coming back from those muscles that are active and going to areas that aren't as metabolically active. That's why when we actually saw the true venous oxygen content right off of those capillaries of those really high intensity exercising muscles, we might literally see zero, like no oxygen left in that blood. But those other areas where it maybe only took 5 milliliters of oxygen or so, they're going to bring the average up so that overall venous oxygen content is going to be about 4, maybe even less in certain cases. Now, remember, our plasma volume is that fluid content, and this is going to be under the natural pressures of the natural chemical, I should say functions, what would be hydrostatic pressure and osmotic and onconic pressures, which means it's going to move accordingly to whatever fluid dynamics that are occurring. So when we're standing upright and we're exercising, we're actually going to see a slight decrease in our plasma volume. And that's partially because of just the effects of gravity pulling everything down in the body. And as we're starting to build up these different metabolites, as we're seeing this increase in mean arterial pressure, we in turn are going to be pulling a little bit of fluid out of the plasma on top of the effects of sweating. So over time, we're actually going to see these fluid shifts. And we went through body composition, obviously, this past week with you guys. What's really interesting is if we had you lay down, and actually lay down almost on like an incline, so your head would be down here and your feet would be up here. And then we had you stay there for like 5-10 minutes and then get up quickly, stand on the Tanita and take your body composition. You would actually probably be rated as having a higher body fat because the fluid shift would go away from your lower body. Now, it's not as bad as when you might see somebody has like really bad lower body edema, which obviously can happen because of those fluid shifts, but it's going to be still a subtle change you're going to see of where you're going to see that fluid moving more in one direction than it should. Now, as we're sweating out that plasma volume, we still have the same amount of red blood cells. So we have now a greater percentage of red blood cells. And this literally means we have this increased hematocrit, which has positive effects in that we're going to have a higher oxygen carrying concentration, which is going to allow us to carry more oxygen per volume of blood, but the negative effect of increased viscosity is going to work against us more than this is going to help. So, how are we going to regulate the responses of our cardiovascular system? Well, it turns out it's going to be stimulated by a variety of different inputs throughout our system. So we're going to see changes in our heart rate, our cardiac output, and our blood pressure during exercise, thanks to initially more sympathetic tone and parasympathetic innervation declining. So we're going to see, literally, we have a activation inside of our neurological system that in turn is going to be increasing our heart rate, having a little bit of vasodilation. Well, remember that's more local, but more vasoconstriction from epinephrine. We're going to have that pressure control system, which we talked about before, where we're maintaining the appropriate amount of blood supply to different regions of the body, so we're not going to get ourselves an issue. But then once we start exercising, we're going to get that chemoreceptors throughout the body to fire, telling the body, or through vasodilation, to get more blood to flow to the areas where it needs to be. So you're going to be able to increase your performance. And this is all working through the wonders of negative feedback, like you've thought or like you've seen before. That's why maybe you guys have been, well, obviously not out as much recently for a while, but whenever you were going to do like a physical event, you could actually kind of feel your heart rate starting to go up before the race even began, or before the match even started, even before the warm-up, because your body has that type of anticipatory response thanks to our nervous system. Now, how all of this is going to work is really complicated, but it's interesting because it's going to work really, really rapidly. And the first thing we need to make sure we're doing is maintaining your blood pressure. We do not want to have too much blood pressure going to the brain, obviously, but we need to always make sure we have enough blood flow going to the brain. Otherwise, we're not going to be able to remain conscious and be able to perform whatever exercise we're looking for. After that, well, now we need to make sure we're getting enough blood flow where we need to our muscles so we can get that physical output. Then we're going to worry about thermoregulation. Then we'll worry about, okay, can we do a little bit more digestion? Or are we making sure everything's being placed where it needs to? Now, this figure is probably a little too small for you guys to go ahead and read it. And I refuse to insult you guys by reading it to you, but I want you guys to take your time, go through it. And if you have any questions about this, we're going to go ahead and talk about this more so at length on Wednesday about how we're going to have the different effects throughout our system, depending on what's going on in the body. So, what's going to happen when we start exercising? Well, the first thing is we're going to increase our ventilation when it comes to breathing. Okay. Now, this makes sense because it turns out we want to make sure that we are getting enough oxygen for the level of output we're about to do. Then we see a second increase in ventilation, and this is going to be caused by chemical changes. This is what's known as the ventilatory threshold. So initially, we're going to start breathing a little bit faster when we just start exercising, but then we're going to start breathing fast enough that we're not going to be able to maintain a conversation with somebody next to you. So this is what's referred to sometimes as the talk test, in that what's going to occur is now, because we have carbon dioxide accumulating in the blood, we have increased amounts of protons because we're using a lot of anaerobic metabolism. Now we're talking about bicarbonate and everything else that's going on with removal there, and some stretch within our right atria as what's going on with trying to get enough blood flow around the body. We're going to start breathing a lot more rapidly because A, that helps with the blood return to the heart through the vena cava, and also it's going to help with that buffering capacity along with delivering more oxygen as it's needed. So you're going to pretty much always breathe at the level you need to in order to maintain that work output. It's pretty much straightforward. So we're going to see at low intensity exercise, you're just going to be taking a little bit bigger breaths, but you're not really going to be breathing much faster. It's once we get up to higher and higher intensities, that's where we're going to be increasing our rate of breathing. So we're literally going to be taking in more breaths per minute. And then once we finish exercise, depending on how difficult it is, this is what's known as excess post-oxygen consumption, post-exercise oxygen consumption, where the longer it takes you to get your breath back after an exercise bout, the harder work you did, and the more anaerobic effective stress you put upon the body that you now have to resolve by helping to buffer it out effectively by breathing. And this is partially because we're getting rid of that excess carbon dioxide. We're trying to get our blood pH back to the level we want, and then potentially a little bit with temperature regulation, but that's not going to be near as big of a key out of those three. Now, why do we care about this? Well, because once we get to that point where we're breathing a lot faster, that's where we're not going to be able to maintain a conversation with our partner next to us. And when that occurs, that's going to be a pretty good indicator that we're starting to dip more into those anaerobic energy systems, which fatigue is going to be coming on, and we might be having our athlete work a little too hard for what their body can maintain. So, myself, when I used to personal train some people that were very large, both of my clients were well over 300 pounds. And we're obviously working towards weight loss. Our post-workout cool down would actually be going for a walk. And, the goal was to walk at an intensity where I could tell it was a little difficult for them to maintain a conversation with me, but not so hard as to where they couldn't keep up the conversation, because then fatigue's coming on pretty soon and they're not going to be able to keep up that work output before they're effectively going to start to fall apart. Now, there are some irregularities that can occur. Dyspnea is what's known as shortness of breath. This is often due to just being in really bad shape. And because we're not able to regulate the level of carbon dioxide and proton concentration inside of the bloodstream, most people are going to be fine. Turns out you're going to be able to get your breath back eventually, but it can be obviously a little concerning for people initially when this start happening, or when this can happen to them, because literally all those secondary muscles, when we talk about the external intercostals, talk about the SCM and otherwise, they start to literally fatigue out. They're not able to keep up that output. And we have then hyperventilation when people are breathing way more than they need to. And this can be because of obviously anxiety about the exercise. We're going to see issues with our blood carbon dioxide going down really low, which could then increase our blood pH. And you can start to feel a little lightheaded, maybe like you're going to faint. And that's why you sometimes see people breathing into a paper bag as a means to calm themselves down a little bit and help bring that CO2 level up a little bit more. Now, the Valsalva maneuver is a natural thing you're going to do when you're lifting really, really heavy loads. And this is where you're going to close your glottis, aka you're not going to allow any air to leave the lung, but you're going to bear it down through your obliques, your transverse abdominis, your rectus abdominis, essentially all of your core musculature, which is going to effectively create what's sometimes referred to as kind of a fluid ball, where that's going to give you more stability in your core, so you're less likely to fold over when you're lifting a really, really heavy load. This also causes your blood pressure to skyrocket through the roof, to the tune of you can be well over 480 millimeters mercury systolic and probably about 300 something diastolic. So hence, it's very contraindicated when you're dealing with really old individuals or individuals that have pre-existing conditions as far as cardiovascular disease, heart disease, because you can literally throw enough pressure through the lines to cause effectively some type of clot to form, which would precipitate a stroke or a heart attack, which you do not want. And also, because of this really high pressure, you're not able to get blood flow to return to the heart like you'd like to, which is going to obviously decrease your cardiac output, and in turn having, drop down the blood pressure a little bit. The highest and hardest I've ever gone as far as with doing the Valsalva with really heavy loads, you can bust capillaries relatively easily in the body. You can pop nosebleeds depending on how high the pressure you go. And then obviously you have that issue of letting go too quickly, which causes that really rapid decrease in blood pressure, which obviously can cause some people to pass out if they're not careful. So once again, you're pretty much going to be breathing at the rate you need to for whatever level of exercise you're doing. Ventilatory equivalence is just looking at literally the total amount of oxygen you're taking in relative to the total amount of air you're breathing in. And you're going to find that point of which you can see that ventilatory threshold where that's an inflection where it goes up. You're not actually taking in more oxygen per breath. You're actually trying to do more with that carbon dioxide than you really are. You're actually becoming less efficient with your oxygen how much you're taking in. You're still taking in plenty of oxygen. You're perfectly fine there. But it's also going to be a situation where we know fatigue is coming because now we're going to use more and more anaerobic metabolism. Getting back to, yet again, that talk test. Individuals that are in better shape are going to hit this ventilatory threshold at a much higher percentage of their max. Individuals that obviously are not as in good a shape, they're going to hit this at a much lower percentage of their max. And obviously I'm referring to aerobic fitness when we talk about what type of shape we're trying to get someone into. Now, as far as, the surrogate measure, what we're really looking for here, guys, is effectively, that point of which where we have an excess accumulation of protons inside the bloodstream. Now, this in turn is going to cause changes in carbon dioxide levels. And when we have both lactate and carbon dioxide coming up, that's driving our desire to breathe, because we can buffer that out a little bit through a respiratory and bicarbonate formation. And effectively, the better way to look at this is going to be what's known as, effectively our lactate threshold or our anaerobic threshold. And this is where you can look at, notice that inflection point where the total amount you're breathing in compared to the total amount of oxygen you're getting in has that point where it's coming up, because we're actually not doing a better job of getting rid of it, but we're actually going to be doing a better job of making sure that we're getting, we're going to maintain about the same efficiency with our carbon dioxide. And that's really what we're looking for here, because we're not able to maintain that same amount of energy output through purely aerobic means. And when you're also looking for this, that ventilatory threshold and the anaerobic threshold are pretty close. So if we took what's known as a blood lactate level, so we can do this via finger prick if we can ever get some new blood lactate strips in the lab so we can go and measure it. But what that will do is actually look at the blood level of your lactate. So if we're doing a good job of staying aerobic pre or just right at the ventilatory threshold, we shouldn't see any accumulation of blood lactate. The second we go above that level, that's getting back to the drain in our tub isn't fast enough for how quickly we're trying to fill it with water. And so our production, how fast we're filling it, is going faster than our clearance, the drain, and so we have that accumulation of lactate levels inside of the blood. So when we're talking about performance, it's pretty rare that your ventilatory ability is actually what's limiting your performance. This actually can happen in like super high level aerobic athletes, but it's pretty darn rare. And yeah, we do require a certain amount of energy to our ventilatory muscles just to keep up these outputs. Now, as far as the resistance to breathing and gas diffusion, it's not really an issue at sea level. It's a bigger issue when we're talking about having some type of restrictive or obstructive respiratory disorders, aka things like asthma, are going to get in the way with our ability to take enough oxygen to keep up the work output that we're needing to maintain. Now, wearing a little mask is going to be obviously a little uncomfortable. As far as how much that takes away from your aerobic performance, that I have not seen any good peer review lit, but I'm sure there's going to be a lot of it coming out relatively soon, since obviously there's a lot of people interested now in how much the masks are chewing people up, I guess, because I guess a little piece of cloth is enough to dominate someone bad enough that they can't breathe, which, that's fascinating. Now, when we're talking about, once again, really, really high level people, there might actually be an issue with not getting in enough oxygen. This is really like the edge of human physiological abilities. And literally the amount of ventilation they're doing compared to the perfusion is not the same. So they literally can't get in air fast enough for how quickly their heart can cycle that oxygenated blood around their body. And because of this, they'll have the exercise-induced arterial hypoxia, aka not as much oxygen in their blood as one would suspect, because they cannot turn over oxygen quickly enough. Now, it's important to understand that your muscles and your blood are trying to maintain relatively thin physiological ranges of pH. If our pH gets to be too low, we're going to have issues with enzymes and otherwise not functioning like they should. And if the pH gets to be too high, same type situation, things are not going to be working as well as they should. So when we happen to be doing a lot of anaerobic work, we're going to be getting a lot more protons in the blood. This decreases our pH, makes it more acidic. And so we're going to try to buffer this to keep this within certain levels. Now, during exercise, we're going to see ourselves moving from being alkaline, so slightly basic, to being acidic. And so obviously that has a pH of slightly lower than 7, 7 being that neutral middle of the ground pH. Now, when the pH gets to be too low, if it's in your blood, you're going to vomit. And the same type situation, pH gets to be too low in the muscles, the enzymes for glycolysis and otherwise are going to shut down, so you can't even get your muscle to contract. You're not going to have enough ATP to do it. And secondarily, the issue you're going to have is it's going to burn like an SOB in order to try to keep up that work output whenever you happen to be dropping your pH down too low. So we are trying to control this pH through bicarbonate, phosphates in your blood, proteins in your blood, and hemoglobin itself. So if we're breathing more, it's going to allow us to bind more hydrogen ions to bicarbonate. And our kidneys are going to also help remove it, and even our stomach acid to a slightly lesser extent. So when we're looking at total capacity of buffering in our blood, notice bicarbonate is doing the vast majority of the work. Hemoglobin is useful and is definitely serving a purpose, as is proteins, and much less so phosphates, but they're all trying to help with getting that pH back to the normal levels. And what's really interesting is by doing active recovery, aka moving after exercise, not just stopping and standing still, you're going to do a better job of buffering out that excess hydrogen ions. So you're going to be able to perform much more quickly. So you're actually getting all of those aerobic, those type 1 muscle cells throughout your body to utilize that blood lactate as a fuel, which is also going to pull the proton out with it. And that's going to help bring ourselves back to a normal pH. So we're going to be able to perform at a higher level. And that's why it's really difficult to explain this to athletes. But after you do a really hard bout of exercise, as long as you're not completely like Tyrannosaurus Rex on your back on the ground, you want to walk around a little bit. You want to move a little bit, because that is going to allow for you to turn this over at a faster rate, which in turn is going to allow you to recover much more rapidly. So when we're talking about the difference between a passive recovery as opposed to an active recovery, you can see this great graphical example in that if you happen to be moving, you're going to get that lactate back down, which means you're going to be able to do another bout. That's going to cause your lactate to go up high again, because like anything else, you tend to hit a point of which you eclipse where you're not going to be able to come back down. So you want to make sure that you're doing that recovery so your athletes are going to be able to perform more and more so. Now, don't get me wrong, having a better aerobic base, so you don't have to use as much anaerobic metabolism in the first place, is very useful, along with making sure that we are progressing athletes appropriately in the program so they're not just being dominated by whatever work they're trying to do. Now, air pollution itself is going to be a major factor in negative performance. Carbon monoxide, which you're going to get from just burning different types of dead dinosaur along with tobacco smoke, and that binds really strongly to hemoglobin, which is going to decrease your oxygen carrying capacity and hence give you a lower VO2. I mean, obviously, you can die of carbon monoxide poisoning. Now, ozone, which is a good thing protecting us on the top of the atmosphere, but as far as to breathe it, same type of situation. It's a rather big irritant throughout throughout your lungs. So you want to make sure you're not around a lot of ozone being created, which is usually due to a lot of like electrical discharge and otherwise in some industrial style work. And then sulfur dioxide, same type situation. It's going to be another type of irritant. There's a lot of other things obviously out there that can and will cause a little bit of irritation to attempts or to normal breathing. And turns out if you don't feel like you can breathe normally, you have a really hard time keeping up your performance and your activity. Now, that being said, we obviously ran through a pretty solid amount of information. Now, when it comes to natural limits to breathing, okay, what type of athletes do you think would maybe have issues with obstructions to breathing, be in positions where it's literally harder to breathe? So they would have to actually get used to breathing against resistance. What type of athletes do you think would have natural potential issues with breathing?
I was thinking about just larger athletes.
Not necessarily, but I mean, if you're talking about like really, really big humans, now you're getting into issues with potential things for like sleep apnea, because literally their neck is so thick that it's effectively choking them out in their sleep, which, yeah, that can be problematic. But, you know, whether or not, I mean, think about it. If you're a 7-foot tall basketball player, are they ever really in a position in their sport where it's literally hard to breathe?
What about like
no.
oh,
Go ahead.
I was just gonna say, what about like a offensive lineman or maybe like a snowboarder or skier?
Okay, what's making it difficult for them to breathe?
Maybe offensive lineman because they're pretty heavy dudes and running around a lot. And I was thinking snowboarder or skier just because of the I can't think of the word now. the altitude that they
Okay,
might be
now
in.
remember, this is a good point. When you're up at altitude, so that's not just, it can be like mountaineers, can be rock climbers and otherwise, it's not actually harder to breathe because actually the air is less dense, so it's actually less effort. The problem is that partial pressure of oxygen is lower, so you're getting less oxygen per breath, but it's not an actual obstruction. So potentially you could have, so Jake put up there helmets and shoulder pads that are a little restricted for breathing. Potentially, potentially wearing a mouthpiece can make things a little bit more uncomfortable for breathing. But there's a couple sports out there where you can get yourself into real situations where it is real hard to breathe.
About swimmers.
Well, swimmers a little bit. You need to make sure you maintain your cadence, and that's an important thing. Keep thinking, guys. Keep thinking. What athletes would actually have potentially frequent issues of where it's literally hard for them to breathe?
What about like boxing or USA or something if someone gets punched in the stomach?
Okay. Oh, good question, guys. Trendon, whenever you get the wind knocked out of you, that's actually a spasm of your diaphragm. So if somebody hits your diaphragm hard enough, aka you take a hard enough hit in the stomach, it knocks the wind out of you. Well, it's because your diaphragm's spasming and you can't breathe normally. That's why it's like, holy crap, like I'm dying for a moment. That's how important it is breathing. But Raquan, exactly. Wrestling and MMA, and I know if you put that out there also, Trendon, think about it. If you're having to wrestle another person, you can obviously be in a headlock. You can be, pretty tied up in really uncomfortable positions where it is literally harder to breathe because you're being choked, because, you're being put into an anatomical position that makes it very difficult to get air. So you guys have probably seen the whole altitude mask that people are wearing. It doesn't mimic altitude at all. Altitude, the problem isn't how much air you're getting in each breath, or isn't how hard it is to breathe in, it's the fact that you're not getting as much oxygen in per breath. So instead, but if you work with like wrestlers, you work with Brazilian Jiu-Jitsu athletes, MMA athletes, there might actually be a point in times to have them train wearing one of those elevation masks because they have to get acquainted with it being harder to breathe when they're in technically difficult positions because they will be used to having to work against that resistance. Does that make sense to you guys? Awesome. So aside from the wonderful reality of, trying to breathe when someone's trying to choke you out, what other types of sports can you guys think of? And I like how you guys put out swimming earlier because that is one where you definitely have to get used to a certain cadence of breathing. But what type of situations, and not necessarily sport, could be just where you're working out where it's like there are things that make the normal breath cycle difficult or different. So you can think the environment, you can think part of the sport, just throw out whatever ideas you guys think of.
Kind of like when you're going to do a heavy squat and you do the Valsalva maneuver.
Yeah, it's really hard to breathe under really, really heavy loads. Absolutely. That's one where you're actually holding your breath as a means to protect yourself, which is a good thing. So you do not decide to herniate a bunch of discs in your spine or jack yourself up otherwise. Now, outside of that, guys, think about how many of you guys have tried to go and do aerobic sports when it's really, really cold outside? How's that feel when you're trying to do that? Yeah, not good. Exactly. Yeah, you can actually, you talk about bronchial irritation when you're trying to work out in really cold air. That can definitely be an issue. What about on the flip side, especially around here in Kentucky, when it can be both incredibly hot and incredibly humid, where, that extra humidity for some reason, plus with the heat, when you're having to exercise at higher intensities, You know, it feels like you're trying to, you know, well, hell, I'm not kidding. It feels like trying to breathe through a wet one of these when you're exercising, which is just, it's just really awkward and uncomfortable. So like anything else, guys, we are finite. We can only produce energy at a certain rate, and we can only, you know, utilize so much oxygen at a certain speed. And we also need to use a certain amount of energy to get our diaphragm to contract, to get our secondary inspiratory and expiratory muscles to contract. So we're going to be able to get in more air. And if they're requiring more energy to do their jobs because you're breathing against resistance, you're in cold weather otherwise, you're not going to be able to have as much oxygenated blood that can go to the tissues you want. So your exercise performance is going to go down. That's why, how many of you guys, and this is not related to the oxygen side, but this is more of talking about the heat. And when we talk about that thermoregulation and blood flow going to your skin, that either when the summer first starts and you start, you know, when you're working out and it's literally hot outside, you just, for the first like week or two, when it actually gets to be really hot, you notice your performance kind of declines in a normal workout, or a normal workout becomes a lot harder. And that's because, well, it turns out we have to send more blood flow to our skin, so we don't have as much that can go to our muscles, and decline in performance. Or the opposite, where now that it's not as hot outside because fall is, you know, showing up, it's going to be a lot cooler. So it's a lot easier to exercise because you're not going to have as many issues with overheating. So any other questions, comments, concerns on what's going on in class and then also in lab this week? Otherwise, I think I might let you guys go a little bit early today, but we're going to talk about one more thing, unless you guys want me to go ahead and discuss any other feature we've talked about here today. Yeah, Jordan, the lab will be due next week. So there's no lab this week. Like I said, I have the assurance of learning day, so I assure that you are all learning. And yeah, so you guys are going to be doing the VO2 submax, so the walk into nowhere on a treadmill. I'm going to have you guys go and get that one out of the way, just because it'll give you 2 weeks to do it, so you got plenty of time. It's going to be a grand total of 3 3-minute rounds that you have to walk to nowhere. Just make sure you wear appropriate shoes and clothes. It's not bad. You can go to the rec center and just find a treadmill by nobody. Obviously, feel free to partner up because it's going to make things a little bit easier for you to do as long as you got a group. And outside of that, sounds good. So I'm going to go ahead and stop my recording.